for two, I guess we can get started with introductions, and if we have any latecomers, they can introduce themselves after, if we get into the thing. All right. So first of all, I would like to thank Rob for being here today and agreeing to do this like last minute. I think Ron had sent an email out maybe like Tuesday or something about it. And Rob was like so quick about saying, yes, I'll be happy to help out. So thank you so much, Rob. I really appreciate it. I don't know if, I don't think everybody knows how the whole connection was made, but it kind of started with Mark Moore introducing us to Rob. And then that was around the same time, I think I started the project with the Wildlife Conservation UAV project, and then I met Mark Page for the first time. He came out to Virginia when General Johan Usti was visiting from South Africa. He's the head of sand parks, and he's the main guy like in charge of security for the park. So Mark met with him, and he was really excited about the project for the blended wing body aircraft that we were talking about designing. And it's funny because back then I didn't really know a whole lot about aircraft or counter poaching or any of that stuff. But throughout this entire process, I've been learning and growing with KWF, the team, and the amazing interns that have come through for several years. So I'm really, excited about having this team come together today so we could talk about some of the old reasons of why OpenVSP was important, but then how it's evolved over the years as well, and how our new interns can take advantage of this tool as a learning tool on Eagle Ray, the aircraft. But I think, once you guys go back to your universities and work on other projects, you might run across the opportunity to use OpenVSP and or similar tools like OpenVSP, and you might opt to come back and use OpenVSP. So, Mark, I want to start by asking a couple of questions about your background, how you got involved with this, and kind of a little bit about OpenVSP. But before we get into that, maybe you can tell us more about your background and how you kind of ended up at Uber, I think is where you are right now, right?
Yes. Yeah. So, and feel free, anybody, to jump in with questions at any time through this. I started with getting into OpenVSP before it was open and even before it was VSP. So when I was in graduate school, our lab had access to a program called RAM, which was Rapid Aircraft Modeler, which had been developed up at NASA Ames. And I kind of, I got involved in using it. I turned out I was the only person who could get it to compile. So I was able to get it to run on more than just the one computer it would run on when I came in there. And I used it for some projects and started getting into this idea of the role of geometry during the aircraft design process. And that moved forward. At one point during my graduate school, NASA Langley came up with some funding and was able to, and this is it's really more of a long story than you need, but some of the key people in OpenVSP's history, the three really key people that I'll mention, are Mark Moore, Andy Hahn, and J.R. Glutamans. And J.R., they all worked together in the same branch back at NASA Ames back in the early 90s. And J.R. was a contractor who was the programmer, and Andy and Mark were really the users. And so the program just got its very early start when it was RAM. There wasn't a budget for it. There wasn't a plan. It wasn't something that anybody set out to do on purpose. It was just something that needed to be done, and they kind of scraped together some resources and got JR to do it as they went along. And then, Andy would go down the hall and say, hey, I've got this thing or this problem, or hey, could it do this? And JR would say, oh, that's impossible. And, 2 hours later, he'd show up with a prototype of it kind of halfway working. And between that and just sort of digging around in the couch cushions looking for some spare change, they found some funding to keep it going and get features added for a number of years. And that was all happening at Ames. at one point along the way, both Andy and Mark left Ames and transferred to NASA Langley in Virginia, and that was, you know, typical family reasons and cost of living reasons. And JR, actually, this is kind of fascinating. He left NASA as a contractor and was a member of a startup of a company called Sport Vision. And if you are a sports fan and you, for example, have seen the dot on the hockey puck in hockey games a long time ago, if you're old enough to remember that, or when you watch NFL football and there's a glowing orange or yellow line at the line of scrimmage and the line of advance 10 yards down, JR has the patents and the Emmys for developing the glowing orange line in football. So yeah, that was his startup. He did that, and then so they got so Mark and Andy went out to Langley, and they wanted to keep supporting and keep moving what was RAM. They wanted to keep advancing it, moving it forward. And back then, it was only available on SGI workstations, Silicon Graphics machines. So they got some money. They found some money and were able to send it out to JR and got him to port it from just SGI only to more generic Unix and also to Windows. And due to whatever reasons, they also changed the name at the time, so that instead of being RAM when it came out to Langley, they changed the name to VSP. And it continued there for a number of years, but still closed. And, you know, like I said, I got to using it as a graduate student and got involved in its development at the end of my time in grad school. And I got to know Mark Moore throughout grad school really well, and Andy Hahn a little bit. And then I came, and when I left graduate school in 2006, I became a professor out at Cal Poly. And I started work doing research, and some of my early sponsored research was on VSP. And I got a contract where JR was a subcontractor, so he worked for me, and we did a bunch of features. And so from about 2006 forward, I was the main person coming up with ideas for VSP, how to improve it, what direction it should take, the vision. Although at that time, from 2006 till about 2010, JR was still writing all the code. Then in 2011, I got the opportunity to spend a year at NASA Langley in person. So I went out and I worked very closely with Mark and Andy and the rest of the group of people at NASA Langley, Bill Fredericks and all those folks. And while I worked there that year, basically Mark Moore and I conspired to get VSP released as open source. And so it took about 6 months of working with the lawyers and trying to pressure them to get it done, and it came down to the absolute wire. But at the end of the year, and basically at the Aerospace Sciences Conference in January, we were able to announce the open source release of VSP. So that was the
Rob,
first
can I jump in really quick and ask a question? So,
Sure.
so I know, I think when you went open source with OpenVSP, the competition was basically, I think it was Xfoil and XFLR5. How were you able to convince NASA and everybody to agree to making this tool available? Because it was bound to change how aircraft design would evolve.
So NASA wasn't really, so NASA really wasn't worried about the competition in a lot of ways. There was some, and I would argue that Xfoil and XFLR5 are still pretty different and have their own spot that's very different. They're still very relevant, and so they're filling different niches. And of course, they were both freely available, so there wasn't a commercial competition problem there. The biggest problem, really, with in terms of the biggest legal hassle of getting it open source, was that at this point in 2011, you know, the code had basically a 20-year history, and that 20-year history of being developed by, you know, while JR had done 99% of it at that time, there were lots of other contractors and lots of other people who maybe wrote 5 lines of code here or did something like that there. And so the biggest thing was that there needed to be a complete legal audit where they went through and they found anybody who'd ever touched the code, and then they had to go back and find the paperwork for how that person was employed. What were the terms of the contract they had with NASA at the time? And then did those terms give that person any right to the code, or did it give all the right to the code to NASA? And so the biggest hurdle was just this bureaucracy, and it's really an interesting story just in the evolution of computer science, and that when this started, people didn't have the same idea as they do today about software licensing and about copyright and about how that applies, and even the idea of open source didn't exist. OpenVSP relies on a graphics technology called OpenGL. Well, in the early 90s, there was no such thing. It was just called GL, and it was a Silicon Graphics proprietary thing that just came with an SGI, because SGIs were really about doing 3D graphics. And so they created this graphics library to let you use their awesome hardware. And there's just tons of examples of this. For example, the way when you click the mouse and you rotate in VSP, the way that we figure out how to take those XY mouse movements and turn it into an intuitive rotation in 3D space is a piece of code called trackball, and it uses quaternion math under the hood. So any of you taking your controls classes learning about gimbal lock, you'll be learning about quaternions. But so trackball was this piece of code that SGI distributed for free. Well, I mean, it was just on the computer, right? It didn't have a license. It didn't have any release. It was just back then in the early 90s, SGI just put this computer on there so that people trying to develop 3D applications wouldn't have to do this from scratch. They'd be able to use that code. And so everything was on the up and up, and it was very legal. But then when you fast forward to a 2011 NASA lawyer's view of intellectual property, they go and they look, well, here's this trackball code with no authorship and no license on it, right? And they're like,
that's brilliant.
right, we can't release this. Where did it come from? There's no license. Where are our rights? And so the hilarious thing about it was I was able to go online and find the exact same code that had been re-released by SGI at a much later date, but with a license at the later date.
Huh, that's clever.
Right. And so there was tons of this through VSP, because that's just how it was back then. There's a number of academic journals, just like Journal of Aircraft or the IEEE journal, or like Nature and Science, the most famous journals in the world. So there's a number of academic journals in the computer science world. One of them is called Journal of Graphics Tools or something like that. And they publish just graphics algorithms and very minutia, things like, if you take a triangle and you have a ray and you want to find the intersection between the ray and the triangle, here's 20 lines of code that do that really well and really robustly. And this was published in an academic journal in the early 90s with no license, because there was no such thing back then. They didn't think about it. So when JR was writing it and he needed to intersect a ray with a triangle, he went and he found this thing and he used it. And again, you come forward to a 2011 view of intellectual property, and NASA says, wait, there's no license on that. You didn't write it. We can't use it. So I did the same thing. I ripped it out. We went and found a modern source for the exact same thing, and then just dropped it back in. So if it's funny, because if you actually go and you take the original NASA download, the open source download, the first one that NASA said, this is OpenVSP, it doesn't compile. It's got gaping holes in it. There's things in it that I just had to rip out and know that it was going to be void so that we could get it over the over the goal line and out the door from the lawyers. And then if you go back and look at the very early history of all the source code, if you look at the Git history of VSP, you go back to the very beginning, it's like, here's the first commit, and then there's me filling all the holes back in. And I knew I was going to be able to do it, but I had to do it after the lawyer's inspection rather than before, because if I did it before, then they'd have to go audit and try and figure all that stuff out.
So you went through a lot of hoopla get it to become an open source software.
Yeah.
Yes, it sounds like a lot of effort went into making this available publicly.
And there are some competitors. You mentioned competition, and there was a little bit of controversy post release. There are 2 or 3 companies that had somewhat similar tools that were commercial tools, and one of those companies, didn't care. One of those companies was kind of annoyed, but didn't really make a fuss. And there was one of those companies where, I mean, they didn't do anything in his company, but there was an individual developer who was really upset that essentially the way they saw it, right, is that the government was releasing a free program to compete with something that they were trying to make money on as a commercial business. And I empathize and I understand that point of view. The contrary point of view is, of course, that OpenVSP and at the time VSP had been developed entirely with government money. And if the government's developing something, then shouldn't the taxpayers have some available access to it?
So what's the so there's OpenVSP is what came out first, and then you it evolved to include, I think, VSP Arrow.
Yeah. So that's the and I'll try and shorten up some of my stories, otherwise we won't get any deep stuff. But so a long time ago, there was a program called VorView, which was a preprocessor that took output files from RAM and then from VSP, and it would process them and set them up so that you could run it in a Vortex lattice called code Vorlax. And Vorlax was in the exact same legal situation that I was talking about, except even more so. Vorlax was a Lockheed Martin Vortex lattice code that was published in a NASA contractor report in either 1976 or 1977. And the reason I mention that specifically is because the law changed the year after it was released and written in that report. And so literally you can find Vorlax by going to a NASA CR and flipping to the back. It's essentially impossible to read, right, because it's a terrible photocopy. But the source code for Vorlax is in the back of a NASA CR from 1976. And by definition, legally, it's in the public domain. The problem was then that, again, back then, people just passed source code around. And Vorlax went from being developed at Lockheed and used by NASA, and it was used at every aerospace company, right? It was used at Northrop and Boeing and small companies and big companies. It was used by the Air Force, and everybody passed it around. And people were fixing it and improving it and doing, expanding it and adding features. And, in the 1970s, the algorithms you used had very little memory, and people hadn't come up with the clever things they have now for things like inverting a matrix. And so Vorlax was very limited in what it could do, and the matrix inversion was slow and not very robust, and there were all these problems that people fixed as it just got passed around and handed from person to person. And so what happened is that when we open sourced OpenVSP, we were able to get and do that audit trail for VSP, and we were able to do that audit trail for VorView, the preprocessor, but we couldn't do the audit trail for Vorlax. We had no idea who had done all these changes over the 35 years since it was officially public domain. And we had no idea the differences between the public domain version and a modern useful version of Vorlax. And it's funny because we were explaining this to Dave Kinney and we were trying to decide what to do. And he basically just said, look, it'll be cheaper for me to write a replacement than it will be to get the lawyers to do this audit. And so Kinney decided to write VSP Arrow.
Wow. So what year was that in?
That was probably, I could look it up. It's going to be around maybe as early as starting in 2010. It may be slightly before the open source release. No, it's going to be after that. So it's probably 2012-ish that he started. So the next and so well, I'm going to jump back a bit. Remember, in the story, I said I went and I spent a year at NASA Langley, the year of 2011 at NASA Langley, and that's when we got it released as open source, and that was version 2.0. The other thing that happened that year is I won another contract with NASA of another 3-year contract to do major work on VSP. So I'd had one before that led to features that ended up in 1.9, 1 point something or other, 1 point, and then up to 2.0. And then I got a new contract. So the new contract was sort of a 2012, 13, 14 timeframe with maybe some extensions in 2015. And that contract, we completely rewrote VSP. So that's the contract that went from version 2 and that was open source to completely rewriting it to become version 3. And that period is somewhere in there is when Dave Kinney started on VSP Aero. And JR was working for me on that contract. But that's also when I went from just being the guy who came up with the features and said, oh, let me give direction and say, hey, this is what you should do, JR, go do it. So I started writing a bunch of code myself in VSP. And my students at the time started involved in development. So, various students like Alex Gary and Joel Belbin at the time wrote things that were significant contributions to VSP. And then since that contract ended, that got us up to, well, at least the first or maybe even the second VSP workshop. And since that contract ended, there've been a number of other contracts and other things that supported VSP development, both from NASA and from the Air Force. And some of it was through a small business that's nearby here called ES Aero. I worked with them while I was still a professor, and we got an SBIR from the Air Force to do some VSP work. And then meanwhile, through all this time, I'm also learning a lot about designing electric airplanes, and that becomes one of my major areas of research. And when I went to NASA in 2011, I was really there working mostly to figure out electric airplane design and work closely with Mark Moore and Andy Hahn and the rest of that branch. So fast forward a little bit again, I took a year off as a professor in 2000. 16, 17 area. I took some time off and was trying to figure out what I wanted to do next in my career. And right about that time is when Mark Moore left NASA Langley and went to Uber to really found the Uber Elevate project. And Mark was the first outside of Uber person hired in to do that. And for the first year, they didn't have a staff, they didn't have a big budget. And so all they could do was hire some consultants. And since I was on a year off and I was sort of someone with some good expertise in electric aircraft, Mark and Uber hired me as a consultant. And I spent a year consulting to Uber Elevate while I was not teaching. And during that time, I worked closely with Brian German, and we ended up doing work that led to a presentation at the first Uber Elevate Summit, where we really sort of laid the groundwork to justify that if batteries got to a certain level of performance, that you'd be able to do the Uber Elevate mission with a fully electric aircraft. And then after that, I continued consulting with them to help develop, well, what were the vehicle requirements? What would be really the set of requirements that you would design an Uber Elevate aircraft to? And partway through that period, as Elevate was gaining momentum within Uber and it was getting more funding and getting set up and they were hiring people, Jeff, who was in charge of it at the time, he was the chief technology officer at Uber, Jeff Holden, wanted to have a team of technical vehicle aircraft design experts. And so they basically talked me into not just being a consultant, but going full time, and allowed me to recruit a team. And so I was able to set up a team, and we actually opened up an office here in San Luis Obispo. So I was able to do it without relocating.
Oh, really? That's pretty awesome.
Yeah, it was
That's really cool.
really everything worked out perfectly. It was the perfect time and place. And so we formed a team to be the vehicle engineering expertise for Uber Elevate. And even though Uber's not building an aircraft, we have a lot of reasons why we need to have our own really solid technical competence. And so that's how I got started at Uber. And since then, the development that I've been doing personally on VSP, I'm still the steward. I still do the release management. I try and answer questions and fix bugs. You'll notice that most of my changes for the last 2.5 years or so have been very much related to things that Uber needs. So
Okay.
just as an example, the propeller component's a lot better than it used to be.
Right. Yeah.
So,
So
it's been that way. But that said, ES Aero has continued getting funding, and they've been doing work for the Air Force now, and have really been doing cool stuff, and have also been driving the general purpose OpenVSP forward. So, development's different. I'd actually think it's pretty positive. There's a lot of maturation that's been going on, where before everything was, very much frantically around adding clever new features, and having me sort of evolved to be more of a user than just someone who's trying to get new features funded, has meant that there's been a maturation, and we're trying to fix more of the bugs and round off the sharp corners to make it more friendly and usable.
so how often do you guys do your workshops?
They've been annual. We skipped a year. Um, I guess 2 years ago, and this year they've normally been in August. This year we're planning it for September, and it's going to be obviously online only this year. And we're working to try and figure out how those logistics are going to work.
Yeah.
So we're trying to figure that out. But they've been annual. The first one, it didn't say first annual. It just was
Right.
the OpenVSP workshop, thinking it might be the only one, and that was in 2012. And we've done it every year except one since then.
Okay, yeah. Well, that's exciting. So hopefully, is it like a new rollout of anything for this upcoming workshop, or is it just the workshop?
Well, it certainly there's not a single like hallmark feature that I could say, but every year at the workshop I take a look at what version number were we at the last workshop, and what version number are we at this time, and I try and summarize all the features that have been added. And it's amazing how much stuff gets added in a year.
Yeah. Eh,
And frankly, it's amazing to me sometimes how much stuff gets added just in each version. And um, I've been working actually with Justin, the guy at ES Aero, who does most of their work on it. And we'll be releasing a new version either today or this weekend. And it'll be 321.2, and it's no wild flashy features, but a lot of bug fixes. And I'd just say in general, everybody should always be using the newest version. There's very seldom any regression or any reason not to, but there's a lot of things that are moving forward that you should always want to take advantage of.
right, awesome. So you think that sums up your long biography?
I
For
guess that I do.
autobiography?
I mean, we're 30 minutes in. I've got plenty of time, so we can go long if we need to, and we can
Okay,
schedule
all
again.
right.
But
Well,
I
how about thank you so much for that introduction. Actually, it's really nice to hear the story, and especially for all the people that do use OpenVSP, and just hearing it from someone that's like an originator of it is fascinating. So thank you for taking the time to go through all of that. But maybe we'll give our team an opportunity to introduce themselves. And then we'll get into a little bit more of like questions and answer session. And if we have more time, I'd love to hear more stories too.
I'm happy to do whatever you guys need.
All right, Sean Bain. Hi, Sean.
Hey there, can you hear me?
Yeah.
Okay, awesome. Yeah, I had to pipe in through my phone, having computer issues. So I guess my role here is as an advisor to kind of help guide this analysis effort from an aerospace and aerodynamics standpoint. A lot of my background is in unmanned systems research and development. Spent 12 years at the Naval Research Laboratory. Moved on since then, working closely with Ron on some very similar types of work, and just here to help provide objective perspective for the students on board here.
Thanks,
Great.
Sean.
Nice to meet you, Sean. Did you know Aaron Kahn?
Oh yeah, I worked closely with him, and Rob, we've actually run into each other a couple of times. I got to go to your 2019 workshop, which was a great event. I really loved it. I started using OpenVSP. I want to say I tried to dabble it in 2010, and when I was at NRL, and it was kind of in my tool belt, as it were. And there were out of my myriad of tools, I used it for some niche functions and put it down for a couple of years. And I really have to say, coming back into it over the last 3 years or so, it really evolved immensely, and it's turned into a really powerful aid. So I really appreciate all your work getting it to the point that it is now.
Well, thank you very much.
All right, thanks for that, Sean. And we also have Professor John Sarr here today.
Hi. Let me, I can even do this for a moment. Let's see. Yes, so I'm a professor of electrical engineering. My background is really more in geophysics, and I became acquainted with Ron about 20 years ago, and that's how I ultimately became acquainted with your project. So my background is not fluid dynamics or aircraft, so I'm kind of an independent voice here, but it's radar, ionospheric physics, power conversion, and actually open source software is something that I'm curious about. I had a comment for Rob associated with his chat about the intellectual property issue, and that is in the academic world, if you get federal funds for some research, one of the things you have to declare at the end of it is whether or not you've invented anything. And the problem is it's such a hassle to do so that nobody ever says they invented anything.
That's exactly right. And your contract agent at your own institution is like, well, how did you spend $1 million and not invent anything?
That's right.
It's like, no, nothing to see here. Nobody invented anything.
All right, thank you for that. Let's see next, who's our John Alberton. Hi, John.
How's it going? Can you guys hear me?
Yes, going well. Thank you.
Yeah, so my background, I'm an aerospace engineer. I went to University of Maryland, got my master's there. My background is really in hypersonics and high temperature gas dynamics. But now I'm working next to Sean and Ron, and in the same office as them. That's kind of how I got involved in this.
Great. Nice to meet you.
Right. Thanks, John. Okay, Ron, I can't find an email from Mark Page. He had forwarded an email that Mark, unfortunately, can't be here, but wanted me to read his point of view, and I can't seem to find it. So, Ron, can you read it and find it? Oh, did you send it to me? Okay, let me see if it's in here. Sorry, guys. Okay. Okay, I think I found it. Here it is. Okay. I'm gonna read this verbatim from Mark Page. And it says, soon after Kashmir World Foundation was founded, Mark Moore introduced me to Princess Aaliyah, and Mark Page participated in a meeting with General Johan Usti, Director of Security for South African National Parks, on the potential benefits of blended wing-body aircraft for counter-poaching missions. Mark was working on various versions of Killer Bee, and we attempted to design an adaptation for KWF. Production costs were too high, so we abandoned the project in favor of more conventional Avenger V-tail aircraft. We are now working with Rapid Composites on use of olefin-based thermoplastics air structures with performance better than epoxy carbon composites, and production time reduced from weeks to seconds. With that, we started the Eagle Ray team. Mark's been one of the main advisors on the design of the aircraft. So we are really grateful to Mark for being part of this. And last week, Mark actually was on a webinar with the interns. I think it was last week. And so was Jay Gunlatch, and the interns that are currently working on the Eagle Ray project. They started, I think, in May, and one, I think Sean, one of the interns, not Sean Bain, but another intern we have is Sean as well. He started, I think, in June, so he came in a little bit later. So they've been trying to wrap their head around aerospace engineering to begin with and designing an aircraft. None of them had any experience previously, but they've been working on a very specific project, and now they're going to kind of like open their perspective on working on more of like a holistic approach to making the aircraft a little bit more efficient. So what I'll do next is let the interns introduce themselves to you as well. So who wants to start?
Hi, I'm Sean. Really nice to meet all of you. I just finished my freshman year at Stanford University, and I was studying aerospace engineering. Yeah, so that's why I was really excited to work on this project.
All right, thanks, Sean.
Hey, so I'm Joey, and I just finished my freshman year as well, and I'm at MIT, and I'm studying computer science and mathematics. And I originally applied to work for KWF to do AI, but they brought me in on the Eagle Ray team, so trying to learn as fast as possible and see what I can do to help.
I just have to add, when I interviewed Sean and Joey, I was like, I think you guys need an additional challenge to AI, because I think both of you came in for an internship with the AI project for our Sea Turtle work. And I just saw potential in both of you, and I was like, I think it's going to be important for you to perhaps at least get the experience over the summer. What you do with it is definitely your choice, but I hope that was the right decision.
Yeah, good.
And you guys are enjoying and learning as well.
Yeah, it's a whole new world, but it's pretty fascinating to learn about, and I'm enjoying it a lot.
Yeah, I think we're missing Max, Akila, and Shreya. We had to change the meeting because of power outage. Surprisingly, we were out of power for over 24 hours, so it was not fun with 95 degrees in the house and no water either. So unfortunately, some of them couldn't make it today, but at least Sean and Joey, I think the two of you probably have done most of the work anyway. So maybe if you have any specific questions about OpenVSP, and if you can talk a little bit more about like where you are right now with the project, what was your first mission, and what are you guys going to do from here on, and what kind of help do you need, or an understanding you need about what the capabilities of OpenVSP could be for you?
So over the past month, what we've been trying to do is substituting in different airfoils towards the end of the wings to try to optimize the lift to drag ratio. And we've mostly been using VSP Aero and looking at the graphs for alpha versus lift to drag ratio. And so now I think we're gonna go for a more holistic approach and start looking at things like trim and twist as well. And I guess we're kind of just wondering what other tools in OpenVSP do you think we should use, and like if you have any pro tips?
Okay, well, there's a lot to that question. First, let me just reflect on some of the folks who've introduced yourselves. It's really great to meet all of you. I know both Mark Page and Jay Gundlach pretty well from the rest of the aerospace community is small, so you run into a lot of the same folks, and I'm really thrilled to see that you guys have such a diverse multidisciplinary team. As much as I love the airplane and as much as I love the aerodynamics, modern airplanes today, particularly unpiloted aircraft like you're designing, are, and it hurts me to say this, right, but it's a dust cover to fly around a payload, right? The reason we have an aircraft is to put this kind of aircraft is to put a sensor in the air and to give it a point of view so that John's radar can go out and see things, or the camera or the IR sensor. And so it's really critically important when you're looking at the design of a system like this to have the sensor point of view involved, and to have that as well. And of course, today a modern airplane, a huge amount of the development of that aircraft is software. And so I found when I was a professor that, you know, a lot of the computer science students at Cal Poly had no idea that there were careers where they could go into aerospace and they could work on satellites or aircraft or sensors and have a long, challenging career in, you know, cutting edge software that was really challenging, really interesting, fun things to work on. That wasn't, you know, the next Pokemon Go app. So I think it's great that you guys have a team like you've described. Wing design, wing lofting is definitely one of the classic and really fun aerospace engineering problems. And so definitely, you know, you're looking to design, you know, a wing that's got a trim, it's got to meet various requirements, and it also needs to, you know, have low drag. And let me see if I can pick which screen. It's going to take a moment. I'm going to just a second. I don't normally use this particular Google product, so I have to give it permission to share my screen. Can you guys see my screen now?
It is starting to come up. Yes.
There we go. Okay. So when you go to design a, give me just a second here. When you go to design a wing, you're trying to, you'd like to minimize drag. You need to, you obviously have to be trimmed, and you need a certain static margin when you're doing a flying wing. So you need it to be stable. And as much as aerospace engineers spend time talking about airfoils and fretting over airfoils, they're in certain ways not nearly as important as you might think. They can drive things, but a lot of an aircraft's, a wing's performance is really fundamentally, you know, driven by the plan form and the shape of the wing. And so in VSP, you know, if I come in here and I just look at setting up a wing, this is really, say, exemplified. If I take a wing like this, just the default wing, and I look at it in VSP Aero, you know, normally we'll look at it with the Vortex Lattice tool, right? And, you know, you can click here to say preview the VLM geometry, and of course you'll notice that the VLM geometry is a thin, we sometimes call it a potato chip, right? It's a smashed down planform, and this airfoil has no camber. So if we come in and we dial in some camber, and we add that in, and so here it's a 2210. Let's make this a let's make it a 2412, right? That's a pretty classic NACA airfoil. So that's a 2412, and we'll go out to the tip and we'll do the same thing there. So this is again an NACA 2412. It's a very classic airfoil, and you know, the camber in this, the amount of curvature here is very slight, right? There's a little bit there, but what I'm really trying to get across is the, you know, this airfoil shape from a lot of aerodynamic perspective, from a lot of aerodynamic performance, that airfoil shape doesn't matter as much as just the plan form and that center curvature line. right? So when you're using VSP Aero in Vortex Lattice mode, and we'll do a quick run here. So we just ran it, and if we come in and you look at the viewer and you look at the solution, here we are, and we just ran 3 angles of attack. So we're looking at the pressure distribution. Since this is a thin surface, right? There's no volume here. What we're actually visualizing is delta CP, right? The change in pressure from the top to the bottom surface. So you're really visualizing where is the lift being created on this wing. And, for a lot of inviscid aerodynamics, so for things like trimming the airplane, for the lift distribution, for the primary structural loads, for all of these things, the thickness distribution of the airfoil doesn't matter that much, right? So now I know Mark Page is really into designing airfoils, and he's very good at it, and he designs he often designs some laminar flow airfoils that are very, very careful about their thickness distribution. But Mark, I think, would totally agree with me in that when you're doing this analysis, right, that it's an inviscid analysis, and meaning no friction. And so that very nuanced thickness distribution in the airfoil that Mark Page has designed doesn't matter for this analysis. It drops out. So and I know that those of you who've had aerodynamics classes as the interns, you both, or maybe it was just one of you, you're freshmen, so you haven't had a lot of these classes yet, but you'll be learning about it, and you'll see that it's really tricky to understand. There's a lot in aerodynamics and understanding what's important and what isn't. So let me just round a little bit. The first thing when you run VSP Aero in this way, the thing that we pop up is the load distribution. This is what we call the lift distribution. And you'll notice that it's the lift coefficient, the local lift coefficient. In aerospace engineers, when we talk about the local lift coefficient, we use a lowercase c and a lowercase l. Whereas when we talk about the total lift coefficient on an entire wing, it's a capital C and a capital subscript L. So you take the local CL, the local lift coefficient, times the local chord, and then you divide it by the reference chord of the whole thing, and that gives you a shape of what the distributed force is on this wing. And it fortuitously, in this case, it looks pretty close to elliptical. But when we talk about an elliptical lift distribution, this is exactly the chart that you want to look at. So you'd like this to be, for low induced drag, you'd like this to be elliptical. But and we can change the shape, right? We can change the shape. We can come into the wing, and we can add a whole bunch of twists. Let's add, and we're twisting about the quarter chord. We normally positive twist is washout, is what we call it. So we'll put in 10 degrees of washout. That's, oh, it went up. So that's actually wash in, it's positive here. So we'll go negative. So trailing edge up, leading edge down is where you normally do washout. So that's a significant amount of twist. But what we'll do is we'll just run again, and we'll get another solution, and notice how different the lift distribution is.
So wow, this is actually kind of leading into one of my questions. So a lot of what our work has been doing is those minor changes. Then you rerun VSP Aero. Is there a feature? This is something Sean Bain actually mentioned to me. Is there a feature that currently exists or that you're working on where VSP Aero saves the results of a past run so that you're able to overlap graphs? Is that something that you can do currently?
So you can't in this GUI. So there is the next version, which will be, like I said, releasing this weekend. It will be set up so that you can, if you run a case in a particular directory, and then you come back to that directory, we're going to add a button here to the results manager that says, load the results. So you'll be able to come back, and let's say you ran a much more complicated case that took 20 minutes to run, and you wanted to come back and look at that solution without having to rerun it. You'll be able to click the button and reload that. It won't add the ability to overlap with a different solution. Now that said, there's different ways to do that. If you want to overlap with the other solution, one is if you just come to if you come over to this here, export to CSV, this button will export all of these results in a comma separated file that you can take into Excel or you could parse yourself. So if you do this export to CSV, it'll take all of these curves that you have, all these convergence curves, all of this data for all of these different quantities that you could want to look at, all these moments and everything else. And I mean, let's just do it. We can just say export to CSV. We can dump it on the desktop. We'll accept that. And then we'll come over here and we can open it with Excel. And knowing my luck, Excel will want to update itself every time I run it. So here's all the data. Here's everything that's visualized in there, right? One way or the other. And so if you want to create some comparison plots, what I'd probably recommend is the easiest way to do it is just write the CSV files out for the different cases you want, and then come into Excel. And for example, that CL times C is this axis here, and the Y is the lift distribution. And so you'd want to plot this row right there versus, let's see, I'm going to try holding Option. Nope. Okay, we'll try this one again. There's going to be a way to select both of these rows, right? And we'll try it with Command. There we go. So using Command, I'm able to grab both of these rows and then come in here and put in an XY plot, something like this, and get a lift distribution plot. So, right, that's for the quick and dirty way to do it. That's what I recommend. Alternatively, if you guys are developing something and you want to get your hands a bit more dirty, you can actually run VSP Aero through our Python API, and all these results are parsed into the Python API and are available in memory from Python. And so you could then use the plotting functions of matplotlib, and you'd be able to plot those things and programmatically access them that way. So there's, it takes a bit more infrastructure, but that's certainly another way to do it. So does that answer your question there?
Yeah, thank you so much. That helps a lot.
So there's a really interesting thing about aerodynamics. And let me see how I can best explain this. Because you know what, you're absolutely right. We need to show you this. I'm going to need two side by side. So I'm going to save this as right here on the desktop. Why is that not? There we go. Let's just give this one a. We'll do that. We'll accept this. And what I'm going to do is I'm actually going to run 2 copies of VSP. And I'm going to go in and open up the first, that one that we did, and I'm going to get rid of all that twist. So we're going to compare an untwisted to the twisted case. We're going to run the exact same VSP Aero cases. And so what we'll have now is oh, we did have camber on this one, didn't we? Okay. So, well, that's all right. Let me, you know what, I'm sorry, I'm improving here. Let me change this back to an uncambered airfoil just to really try and tell you guys this story as crisply as I can. So here, one of these cases, which, Lord knows which one it is because we've got too many windows open. So one of these, we now have 0 camber, and the other one, we now have 0 camber. So one's twisted and one's not. They both have 0 camber. And so in this one, we'll go and we will run VSP Aero. And in this one, we'll go and we'll run, we'll run VSP Aero. And I want you to look now at, and what we're really going to want to do, that's annoying. There we go, is compare these two charts. So can everybody see what we've got? So the one on the right is the one without camber. And the reason I know that is it is an uncambered, untwisted wing, which means it's completely symmetrical, which means that when we run it at 0 degrees angle of attack, there's going to be 0 lift. It's a flat plate, so it's 0 lift. And that's why the lift distribution, these red dots for the 0 degree angle of attack case, it's perfectly flat. Okay. So I know that this one is, this perfectly flat is our uncambered, untwisted case. This one, all we did was we twisted the wing, right? There's still no camber. And notice that we now have, and we twisted the tips down 10 degrees. 10 degrees is a lot, but we moved we twisted the tips down 10 degrees. And so now notice that the lift distribution is now negative, right? It's negative over the whole thing, and it follows this complicated curve. So here's some fascinating things that they don't teach you about aerodynamics until you really know what you're doing. So this is some good stuff. This red curve is what we call the basic lift distribution. It's typically the lift distribution of a wing at 0 angle of attack. And we also have the concept of what we call the additional lift distribution. And the additional lift distribution is the delta, the change in the lift distribution as you change angle of attack. So the one on the right, if you take this, and I'm bad with colors, I'm partly colorblind, so we're going to call this one yellow. If we take the yellow curve and we subtract the red curve, right? If we take the yellow curve and we subtract the red curve, and that was for 5 degrees. So usually you then divide it by 5. But if you can imagine, you take the yellow and subtract the red and you divide by 5, we would call that the additional lift distribution. And one of the neat things about this kind of aerodynamics is as you go from 0 to 5 and from 5 to 10, this is the exact same delta. The delta from the red to the yellow is exactly the same as from the yellow to the green. Okay. And what'll really blow your mind is the additional lift distribution, right? The delta between these curves is only a function of plan form, i.e., what does the wing look like when you look at it from the top? The additional lift distribution is only a function of plan form, not camber, not twist, not airfoil. And these two wings, they have the same plan form. So believe it or not, the delta between the red and the yellow on the right-hand chart is actually the exact same as the delta between the red and the yellow on the left-hand chart. Okay. So, and it's also the same as the delta between the yellow and the green. So again, the basic lift distribution, which is the red line, depends on both the plan form and the airfoils, both the camber and the twist, right? The red line depends on the camber, the plan form, the camber, the twist, whereas the deltas, the changes between them, only depends on the plan form.
Rob, I think Ron has a comment here. Says perhaps you could discuss the impact on stalling.
Sure. So let me make a note of that, and let me get back to that in just a minute, Ron, because that is a good point that it comes in. And flying wings, this becomes really critical. But what this really means is when you when you twist a wing, right, when we put 10 degrees negative angle of attack out here at the tips, you know, it made this change to this basic lift distribution, right? It brought that down, negative at the tips, positive at the root. And it changed that shape, but you're not changing the deltas between it. So there's a lot of things that flow from that. And in fact, I've got some papers on wing design that I think actually, Ron, you mentioned in one of your emails that you were interested in tools that could sort of automatically jump towards designing a wing for a particular case. And there's some math in there that essentially there's some things you can do to do what you're asking. It's not, you know, a canned push button tool, but there are some neat things that come out of it. This wing that we're looking at has pretty good stall characteristics. When we're interested in stall from a lift distribution standpoint, we probably want to look at this chart, the little CL. So not multiplied by chord, but just the little CL. So that's the local lift coefficient. And what we want to watch for, this is basically how hard we're working each section. And what we want to watch for is how high do these sections get? If we're using an airfoil that stalls at, let's just say that we had an airfoil that stalled at local CL, little CL of 0.6, then we would look at this kind of a distribution and we would say, oh, then I expect the wing to have stalled from about, you know, this, we'll call it 20% to 60 or 75% chord, right? In this region, we expect it to have stalled, but out here at the tip, it has not stalled, right? So we can look at the CL distribution, and let me give you a, and if we look at the other wing that's not twisted, this is a much worse case, because here, again, if we look at the CL and we said it stalls at 0.6, first off, much more of the wing is stalled. Now you could say, oh, well, you know, we're getting a lot less lift because we've twisted it down 10 degrees, and that's true. So you don't necessarily want to, in aerodynamics, you don't want to compare at angle of attack to angle of attack. That's the first rule. You don't care what the angle of attack is. The angle of attack is just, you know, somebody walked down the side of an airplane with a paintbrush and drew a reference line. And right, the physics don't care about your reference line. The physics don't care about angle of attack. The physics care about lift coefficient. They care about stall, and they care about drag coefficient. So when you compare two drags, you want to compare them at the same lift coefficient. And in this case, what we're seeing here is this airplane on the right with no twist. When it stalls, it's clearly going to stall outboard first, right? It's going to stall out here at the tips. And tip stall is bad, right? That's the short version. But the reason tip stall is bad is out here at the tips, that's where you put your ailerons. So that's how you have roll control. That's how you have the ability to tip the airplane left and right, to roll the airplane. And worse than that, stall doesn't happen at the exact same moment, right? Stall is going to happen, say, when you're on an approach and you're on base and you're turning base to final. So you're in the middle of a turn, you're turning into a headwind, there could be a gust, and you're at very low speed. So you're on the verge of stall, and you're turning base to final, so you're close to the ground, right? You're about to land. And what happens is that one wing is going to stall and not the other, right? Because it's this you're on this prefaces. So one of them is going to stall and not the other. And what that means, if it stalls on the tip, think of it as a moment arm. If one stalls and not the other, that wing is going to dump out, right? It's going to drop out from under you because you've lost lift way out on that tip. So you're in there, you're turning base to final, and you lose the lifts on the tip. That wing's going to stall, and basically you're then going to tumble and you're going to crash. Whereas the airplane on the left, we could make it even more, we could make it even better. But let me just go, let's see, let's try the airplane on the right. Let me see, which one is this? This is the one without twists. So, so here we are. This is the one without twist. Let me change it to be unswept, and let me change it real quick to be a Hershey bar wing. So this one, let me just say, and rerun VSP Aero. So this is a Hershey bar wing, and notice this is its lift distribution, but when we look at the sectional CL, see it looks much more rounded. It's high in the middle. And so this wing, when it stalls, it's going to stall in the middle of the wing. So you're going to lose that lift in the middle, which doesn't have that moment arm. And so when you stall this Hershey bar wing, this rectangular wing, it's going to feel very mushy, right? You're going to lose lift and you're going to go into that stall, but it's not going to cause a big rolling moment. And so this Hershey bar wing is going to have a very benign stall that that doesn't kill anybody, because the pilot will feel it stalling, and it's just like like driving a bicycle onto a beach, and you're driving into the sand, right? And it gets real slow and it slows down. Whereas the other one, it's just instant wipeout, right? You don't have any warning and it takes you out. So, this is the kind of thing you can do with these lift distributions and that you can understand. Now, a normal airplane, let me close this other one just because it's too confusing for me to have two open at once.
Rob, can I ask John Sarr's question? I don't, and you could keep going with what you're doing, but I just wanted to ask his question. And his question is, does the Python API permit multiple runs by scanning a parameter for optimization purposes?
It takes some work, but it's certainly possible. There's not a single call that just says, sweep this parameter from A to B and run a bunch of cases and collect the data and put it in this pandas container, right? We don't have that high level of a function call, but certainly you can change any parameter in VSP in a model, both the VSP Aero solver parameters as well as the geometric parameters, and you can access all the data. And so it's kind of a DIY, but you can write a for loop, you can change the parameter, you can track the data, and then you can create a plot. So there's not high level functions for doing design sweeps, but it's absolutely what it's there for.
So it definitely helps Joey and Sean, both of you are also doing computer science, because then some of these things can be solved by you writing your own code.
Right, we'll definitely have to look into that.
So a normal airplane, right, with a wing and a tail, has the main wing is set up to be lifting. Obviously, you need lift, but the horizontal tail is actually either downward cambered or at a negative angle relative to the wing, or is pointed down, or is an upside down camber, right? So it actually has a down lifting force, right? And so a normal airplane, the tail is fighting against you, believe it or not. And the reason is to make the airplane stable. It's to get the moment behavior the right way. And you're going to have a center of gravity of this airplane. And I don't have a, let me add a blank. And if we want to represent where that center of gravity is, so we'll say that center of gravity is about there. I'll move it vertically a little just so that it stands out a little bit more. But so if the center of gravity is here, a stable airplane, what you want is when you perturb it, when you bump it, or you change its angle of attack, you need to know, is that disturbance, is that going to continue to grow, or is it going to damp back, and is it going to go back to zero? And the perfect example of this, let me here it is a dart, right? Have any of you played darts before, right? So a dart is just a really terrible airplane. And what you'll notice, right, is it's got the tail in the back, right? The fins are in the back, And the center of gravity is right somewhere way up here in the front, because you've got this big brass section, right? So all the weight's in the front and the tail's in the back. And the reason you do that is because it's going to pivot around the center of gravity, and the fin in the back, that means that its aerodynamic center is all the way in the back. And I used to do this demo in class. I don't have a piece of foam board here. I've got some cardboard, so I might be crazy enough to do it. But if you take like a piece of 2-inch insulating foam that you would have on the side of a house or something like that, and you actually take a dart and you throw your dart backwards, standing a normal dartboard distance away, your dart will flip over midair and will go into the foam correctly. And that's because it is stable. It is so stable that if you throw it backwards, it's going to correct itself. So, and not only that, if you can get a friend to throw it backwards and you stand where you can watch its flight from the side, you will not only see it flip over, but when it flips over, you will see it oscillate and that oscillation damp out. And that's what we call the short period mode of an aircraft in flight dynamics. So you'll learn about that in 2 years. So that short period mode is its static stability. And the more stable something is, the quicker that'll damp out. You don't want to play darts that way because it doesn't damp out fast enough to get a good accurate target. So I don't recommend it for winning dart matches, but it is a really cool demonstration. But it tells you that, right, to have a stable airplane, you need the tail in the back and the weight somewhere up in the front. And what it doesn't tell you, the reason I said a dart's a really bad airplane is, imagine, right, the purpose of a wing is to get lift equal to weight, right? We need a force. We need an upward force, a lift, to counteract the downward force. So if we want to get lift to counteract the weight, the only thing I have to do lift is these tail surfaces, right? So imagine if I put a whole bunch of lift back here, how do I counteract that weight vector, right? I can't. So the tail is great for stabilizing the airplane, but to make a dart into an airplane, let me see what I've got here. I think I've got some. There we go. Just a 3x5 note card. If I wanted to turn, I'm going to fold it in half so it'll look like a decent airplane. If I wanted a dart to be an airplane, I'd need a wing up here, right? I'd need a wing on top of that CG so that most of my lift was now centered over the CG, and I got my lift vector to counteract my weight vector, and those could cancel out, and I'd get something that could fly and hold itself up. But I've still got the tail back here in the back to keep the nose pointing forward, to keep it stable, right? So that's how a normal airplane works. Now, the subtlety, I mean, there's plenty of subtlety, but some of the subtlety comes in that if I didn't have this tail at all, and I just had this wing, what would happen is I would have that lift, but when I increase the lift, the moment, depending on exactly where the CG is, would either stay the same or it would actually increase. And so when I get that perturbation, when I hit a little bit of wind and I increase that, it would then tumble, right? It would just keep going. And take your dart, and take the tail off and then go and throw it and try and get it to stick in that piece of foam. Right, and what you'll find is that without the feather on the back, it won't stick. It'll tumble, it'll hit sideways, and it won't stick into the foam. Right. So this is a little long-winded, but this is how normal airplanes work. And what you'll find is if you do some free body diagrams and you draw the forces on this, I also said. Yeah. Do you guys see my video or do you only see my screen?
I can see the video and your screen. I just kind of, I don't know if the rest of you saw it, but I made your video big because I wanted to see your demonstration.
Yeah, I'm sorry. Well, I'm glad it at least was there. Otherwise, I was just waving my hands around like a maniac.
No, definitely watching. I think this might be in context to what you're talking about also, Rob. Ron's question was, could you discuss reflex within the context of your body tail context?
Well, that's exactly where I'm headed. So in order to trim an airplane, so in order for it to be stable, the tail has to be in the back. But in order to trim it, you need to get it to a situation where it has a positive total CL, but a 0 total moment. Okay, you have these two conditions for trim. You have your CL and your weight counteract, right? So you have lift equal to weight, so that your sum of the forces in this direction are 0, and your sum of your moment is 0. And so the tail is kind of taking care of the moment, and the wing is taking care of the lift. And what ends up happening is that since the wing is up, it's creating a moment that wants to go and cause the nose up. I'm sorry, it's backwards. It's actually creating a, I'll have to write it down. But so the wing is creating a destabilizing moment. And the tail is stabilizing, but you need that tail at a negative angle of attack. I can derive it, but trust me for now. So that gets us, you guys are designing a flying wing, right? Let me cut to the chase and what Ron wants me to talk about. On a flying wing,
I think it's blended wing. If you could actually maybe even talk about the difference of what would be considered flying wing versus blended wing.
yeah,
Slightly different, right? And that, at least that's my understanding.
I'm gonna give a snarky answer. It depends on whether you come from Northrop or whether you come from Boeing.
Okay, okay, fair enough.
Jack Northrop was the originator of the flying wing, and you know, obviously Northrop makes a lot of flying wings. They made the B-2, and they made a bunch that were experimental back in the 40s and 50s. Boeing, which really is the Southern California Boeing, so that's Heritage McDonnell Douglas and Heritage Douglas. There's a guy there, Bob Liebeck, who's really the father of the blended wing body. And so Bob Liebeck has been pushing the blended wing body concept for many, many years as a commercial transport airplane. And, you know, and then Mark Page used to work with Bob Liebeck, and they're friends, and that's where Mark learned about that. And so Mark comes out of a, you know, Heritage, Boeing, Douglas, Southern California background. And so for him, a flying wing concept is a blended wing body. Whereas somebody who came from a Northrop background would call it a flying wing. From the physics of just an airplane, just looking at it from the outside, they're the same thing, right? And what I want to really get across here is, for an airplane to be stable and lift, right, you need a down force aft of the CG, right? You need a down force aft of the CG. And so let me go back to our example file. And here in our example file, where we've twisted the wing down, right, where we've twisted the wing down at the tips, that's essentially this outboard. You can think of the tip of this wing is acting like a horizontal tail, right? The tip of this wing is after the CG, because the CG is going to be up here someplace, and it's pushing, it's twisted down. Whereas if you took this wing and you and we took out that twist, this would be unstable. Okay, and we can show you that. Now there's other ways to do it. There's two ways to achieve this, and when we talked about camber in the first place, right, we went to a 4412 airfoil, and this is an airfoil with what we call positive camber. And so let me just come in here and really exaggerate that camber so that you see what I'm talking about. Right, this is a positive cambered airfoil, and the way a positive cambered airfoil works is it has its own moment coefficient. And so adding camber to an airfoil not only adds lift, but it also gives that airfoil a moment coefficient. And a positive cambered airfoil like this has a destabilizing moment coefficient. So this airfoil alone, if you just went and made and somehow you could fly a 2D airfoil, it would be unstable. Whereas if there's zero camber, the airfoil itself is neutrally stable. Okay, and so what you can actually do is you can have, I'm not going to be able to do this with. This is going to get a little complicated, but if I come in here and I adjust my airfoil up a little in the front, but then down in the back, I can have, and this is very crude, but you see I have a camber line that goes up and then down, and then it comes back up to the trailing edge. So doing this, and you'd really probably want it more like that, right? Having this rapid, this rather distinct upward curving camber at the trailing edge, that's what Ron was talking about as a reflexed airfoil. So normally the camber of an airfoil would be up in the front, but putting that camber up here in the front is destabilizing. But then you put the reflex in, and that makes it stabilizing. And this is a little, you could think about it in context of what we were just saying. I said to have a wing be stable, you needed some negative lift at the back. Well, look at what this airfoil is doing. By sloping back up, it's creating negative lift at the back. So, right, we're creating positive lift up in the front where we need lots of lift, but then we need negative lift at the back to counteract that moment. So there's kind of two ways to make a flying wing or a blended wing body stable. You can use reflexed airfoils, where you have these airfoils that come back up in the back to counteract that moment and balance it out. Or you can use sweep and twist, right? So if you want to have, or you can use a combination of them, right? They're not exclusive, they come together. But so if you want to design a flying plank, right, a Hershey bar that flies, then there's no sweep. And the only way you can get that stability is out of the airfoil itself. And so if you have a flying plank, an unswept, Hershey bar kind of shape, then you have to have, right, if you have if this is your airplane, then you absolutely have to have reflex airfoils in order for it to be stable. And this can be done. And what I'll tell you about doing this is it's very tricky, right? It's very sensitive, because you'll end up with an airplane that has a very narrow permissible CG range. Now, for a UAV, that may not matter, because let's say it's an electric UAV, so the batteries are always the same weight. You're not burning fuel as you go, and you're always flying it with the same payload. So you could say, okay, well, the CG is always in the same place. We know that. We don't need a big CG range. Whereas you can imagine like a big transport military airplane where they're going to load like Humvees in the back, right? And the next time they're going to load a tank, or maybe they're just going to have a bunch of dudes, or who knows? Maybe they need to deliver 10,000 ping pong balls. you never know where the CG is going to be on a day-to-day basis. And so that transport airplane, you need it to be able to handle a wide range of CGs. And for that, you'll pretty much always have a normal wing and a tail, because that's the best way to get lots of stability. So most blended wings and most flying wings will use a combination. They'll have some amount of sweep, right? They'll have some moderate amount of sweep in them, and they'll have some amount of twists. And they'll maybe have, they're not going to have hugely cambered airfoils. Because having a lot of camber in your airfoil is just adding a very strong destabilizing moment that then you've got to counteract with more twist and more sweep and more reflex. So you're going to start with less destabilizing airfoils. When I was an undergrad, so back when I was in college, my senior design team designed a flying wing. And, we didn't have VSP, we didn't have a lot of sophisticated tools, and we were faced with the same thing. And I was the one who was sort of doing this part of the design. And so we had this choice of, are we going to design it around, are we going to use twist and sweep? Or are we going to use twist and reflexed airfoils? Or sweep and reflexed airfoils? Or are we going to use both reflexed airfoils and twist? And what we decided at the time was that it was harder for our tools to predict the detailed moment of the airfoil and the reflex influence. And we were less confident about our ability to build, because this is something we were going to build and fly, with our own hands and not much skill. So it was harder for us to build something that really got the reflex perfect. And so we made the choice to use symmetrical airfoils. So we didn't add any camber in at all, but we used symmetrical airfoils because we knew that the moment that they would contribute would be 0. So it wouldn't be bad, right? We didn't do anything bad with them. But then we just used twist and sweep to get our stability. And so that was a choice that we made. Now, you've got somebody like Mark Page, who's really good at airfoils, and you've got X-foil available to you. And so I wouldn't be as afraid as I was back then at the negative moment and about the reflex. I think going at it with a combination of reflex and twist and sweep is a reasonable way to go. Let me show you something very directly. When you're doing VSP Aero, there's this screen here where you can put the moment reference position, right? You can put the moment reference, and by default, it's just at 0, 0, 0, so it's at the nose. But that's not where the CG is. So if you're building up a model and you know where your CG is, by all means, just dial in this X and say, okay, I want my reference position wherever that is. For today, we're going to calculate where the CG is according to VSP. And so it says it's 3 inches or 3 units back from the nose. And I think the chord was 4. So this fat airfoil out here at the tip is really throwing that off. But let's reduce that a little. So let's put it at 2. And we're going to run VSP Aero. And I'm going to look over here at the sweep tab. And that's where we're sweeping, the chart is sweeping the 3 different runs that we had. And on the x-axis, I'm going to plot our moment about CMY. And on the y-axis, actually, I'm going to flip those. I'm going to do CMY on the y, and I'm going to do CL on the x. And this chart is what you want to look at to talk about stability. Okay, this is the main chart about stability of an airplane.
John has a question. He says, is a negative lift wing less sensitive to stall?
So you got to have positive lift, because lift has to counteract your weight. So definitely twisting out of the tips can, reduce that tip stall. And so those go hand in hand. In terms of reflex, I'd have to look really closely at whether reflexed airfoil had a different stall situation than a more conventional airfoil. I'd have to think about that and look up some numbers. Let me go back into this wing real quick. And this crazy airfoil back here that we've done at the tip, let me change that to a more conventional airfoil. Let me change that back to just something plain, and again with no camber. And here we're going back to an uncambered plan form with just twist. And we've got the twist in there. Sorry, we've got 5 degrees. We'll leave that at 5 degrees. I am going to put back in that taper that we had in the original wing. Maybe not quite so much. And I'm going to add a little bit more sweep. I'll go to 25 degrees. And I'm going to rerun VSP Aero. And I'm going to recreate that chart that I was just talking about. So CMY versus CL. So this is the important chart for trim. And let me explain why. And I just did it backwards again, didn't I? CL and CMY. This is how I want it. CMY on the vertical. So in order for the airplane to be trimmed, right, that moment, and now our moment center is our CG, right? Our moment center about the CG needs to be 0. So this airplane, we need to find where CMY is 0. So that comes this line right here, right? That line. And then we look at where that line intersects, and that is at some CL, right? In this case, it's very near to a CL of, I'd say, if this is 0.2, that's 0.1, that's 0.05. So very near to a CL of 0.05. That point, which isn't even in the point we analyzed, but where this line crosses the horizontal axis, that point is where this airplane would trim. Okay, that is the point where moment is 0, and it's going to trim at that CL, that 0.05. Now, you have to satisfy, is that CL the CL you want it to be? And so what you do is you look at that CL and you look at the weight of your airplane. And of course, CL of the airplane is weight divided by QS, Q being the dynamic pressure. So weight divided by 1/2 rho v squared times the wing area S. And the important part of that is the V squared, right? There's a velocity in there. And so what that means is there's an expression when you learn to fly, which is pitch for speed, right? When you talk about your airplane, when you're at high angle of attack, you're at high CL, and in order for the airplane to trim, for that to work out, you have to be flying slow. Okay, and when you go to low angle of attack, you're at lower CL, and in order for the airplane to trim, you have to be flying fast. And so you might think that the way you control the speed of the airplane is with the throttle. Okay, you might think that more thrust means more speed, but that's not actually true. This is one of the most counterintuitive things. When you go to learn to fly and you're taking your first flying lessons, this is one of the things your instructor has to drum into your head. Pitch for speed, throttle for rate of climb. And so by varying that pitch, by varying CL, that determines what speed that airplane's going to fly at, not the throttle. And then when you add more throttle, what that'll do is at the same speed, that'll cause you to climb or to descend. And so if you want to stay at the same altitude, then you adjust the throttle just right until your rate of climb is 0. So you could really think, right, most of an airplane's flight, think about like flying across the country to go visit grandma or something, right? You're in a 737 and for 4 hours while you fly over Oklahoma or someplace, right? In that situation, you're in equilibrium, right? You're in that moment. You're for the whole thing for 4 hours. It's really boring because lift equals weight, thrust equals drag. And so the adjustments that the pilot's making are incredibly subtle, right? They fly most of it with their hands in their lap. You know, they're not hands on the controls all the time. And it's not entirely that it's because there's an autopilot. It's just you let go, right? Because you have a trim wheel. So you've got your main elevator control is the stick or the yoke that you move back and forth. But you also have a trim wheel, which is a little knob that you turn, and it's on a friction wheel, and that adjusts the trim tab. And so that's a sort of this fine adjust, right? You can always grab it and jerk it around, but you've got this fine adjust. And so what you do is if you want to fly the airplane at 200 knots, you hold the yoke and you move the yoke until you're flying at 200 knots. And then you move the trim tab, and to do that, you're having to put in some force. So say you're having to pull with 3 pounds of force, and you feel that as a pilot. And you're pulling with 3 pounds of force. So then what you do is you reach down to your trim tab, and you roll in some trim. And as you change the trim, to stay at that 200 knots, you need less and less force. Until you get to just the right amount of trim, and it's 0 force, and you can let go. And now the airplane is trimmed at 200 knots, right? And likewise for throttle, if you're climbing and you don't want to be climbing, you pull out the throttle a little. You put in a little less throttle. And if you do too much, then you're going to descend. Well, okay, if you're descending and you don't want to descend, then you give it a little more throttle. And you adjust it until you're flying along, hands off. The throttle's on a friction knob. It's not going to move. And the trim is on a friction knob. It's not going to move. And you're in trim. Your airspeed is in trim, which is lift, and your throttle is in trim, which is drag. And in that trim, if you want to go a little faster or you want to climb a little, let's say air traffic control comes on and says, hey, would you climb and speed up? You don't even have to touch the yoke. You can just reach down to the throttle and you say, okay, I'm going to move the throttle forward a little, and you're going to start climbing. And if you need to speed up, you can roll in a little more trim. You can put in some nose down trim, and the airplane will start to speed up. You don't even have to touch the yoke. You can do it all through the trim controls. And it's all about adjusting this very subtle equilibrium. So in VSP Aero, if I were to put control surfaces on this airplane as an elevator, and if I were to look at an elevator undeflected and then like 1 degree and 2, 3, 4, 5 degrees, each of those different deflections would create another line parallel to this one. So this is my 0 degree line. And then I'd have a 1 degree line over here to the right and a 5 degree line, and they'd all move, and they'd actually move up and to the right. And what that's telling me, right, is that with my 0 degree deflection, this is my trim point. But again, if you can imagine, if I then deflect the control surfaces, I've got a parallel line over here. It's going to intercept this vertical axis, this 0 line. It's going to intersect it at another point, say over here. And so that other control surface point is going to have a different trim point, right? 0 moment is going to happen at a different CL. And so I control what CL I'm flying at by controlling that control surface, which I'm doing by dialing in trim. I know it's like a fire hose right now. And right, to design a wing and to get it all right, you've got to basically handle all these things at once. You need to figure out what speed you want to cruise at what weight, and with what weight area. That gives you a target CL. And then you need to twist the wing or put in enough reflex so that you are trimmed at that point. And the slope of this line, here's another little trick. The slope of this line is actually your static margin. It's how stable you are. So this line in this CL, the slope of this line, if it's very, very shallow, it's less stable. If it's a horizontal line, it's neutrally stable. And if it's sloping up and to the right, then you have an unstable airplane.
John has another question. For max fuel efficiency at level flight, there must be an optimal trade-off between throttle and trim, or does max fuel efficiency bump into stability issues? Oh, never mind. You just answered it.
No, that's okay. Typically, depending on whether are you designing electric airplanes or using a fuel burning engine? Okay, they're all electric. So
Yeah.
the reason why I ask is jet airplanes and then piston engine and propeller powered airplanes and then electric powered airplanes. There's some subtle differences in whether you want to fly at the best L over D or whether you want to fly at best CL to the 3/2 over CD. And there's some subtlety in there about your best range. And then there's the question of, do you want to fly at best range, or in your case, since the whole point is to get a sensor in the sky for a long period of time, you probably want to fly at best endurance. Or you may want to fly part of your mission. Let's say you want to patrol an area that's far away, then you want to take off. You want to get to that area at, you want to fly best range speed to get to that area. And then once you're there, you then want to fly at your best endurance speed. So, so in that case, what I would say is and let me change this plot to a drag polar. So the x-axis needs to be our CD and the y-axis needs to be CL. And if we ran it with more points, let's go ahead and do that. And we'll run it with, you should never run it with this many points, right? It's just not necessary, it's wasteful, but I'm trying to make a point. So it's pretty quick here, so we'll just do that.
So,
Go ahead.
I was just going to say, so I know you gave a really good example of, like, let's say we start in one location. I'm going to use our Malaysia project as an example for this. So one of the challenges they face in Malaysia is trapping sea turtles in pens inside the ocean. And then when the Chinese vessels come through and they poach all the turtles, because in the past when they used to leave them on the islands, the turtles would die because they would run out of food and they would need to be in the ocean. So the aircraft, one of the missions for this particular aircraft, Eagle Ray, would be to be able to fly around the different islands, but we would leave from like one location and go around an entire island. So now, we might face a variety of wind conditions as well. So, depending on how far we're going, that the endurance is definitely probably more important for us than the speed would. Because yes, it's kind of cool to have a really fast aircraft, but like you said, we want to be able to fly over the ocean, look for these pens which illegally trap sea turtles in them, and then use AI to scan inside and be able to determine, are there sea turtles trapped or not. If there are sea turtles trapped, then we could report that to the local authorities and they could go out and do their part. But yes, at that point, that speed is not going to be necessary, but the ability to fly around multiple islands would be critical.
So I think I really well put, and what we call that in aerospace is that your ConOps, right? This is your concept of operations, and having a really well-defined ConOps and really understanding your ConOps is really important. And so let me put some subtlety and just let me emphasize what you just said. You're going to take off from point A, and you need to get to an area where you want to patrol, and your sensor's not even on. You want to get there. Again, it's not about speed, but you want to get there, get the range as efficiently as possible. So you're going to fly at a speed for best range over the area you're uninterested in, right? Now, there's two different kinds of patrolling that you might do, right? Let's say, and again, I'm just going to make some things up and we can talk about how it applies. But let's say we're patrolling a beach and we're looking for unknown traps. So now what I'd like to do is, my metric is how many miles of beach line can I cover in a certain amount of time, or on a certain amount of charge. So if I'm searching for something I don't know where it is, then I probably want to fly at the speed for best range, because my metric is how many miles do I cover. Because if I can cover more miles of beach, then I want to fly at the speed for best range. Whereas, let's say we spot a trap that has some turtles in it, but for, we're recording this and we're going to use it in a court case, and so to be able to have ironclad evidence that these are the bad people that are the ones who placed the trap, we want to keep continuous video coverage. We want to circle that one trap and keep video coverage on them until the authorities show up and arrest them, right? And so now, but we don't know how long the authorities are going to take. So now we're not patrolling. We're not going and looking for other traps. We're not trying to cover as many traps, as we can. So our metric is no longer miles per charge of battery. Now in this moment, now we want to just, how long can we circle? And it's all about time. And so when you're observing a single location, your metric is typically going to be how many hours per battery. Whereas if you want to go and patrol a coastline or do a grid search, then it's how many miles per battery. And from the aerodynamics and from the aircraft performance standpoint, those two speeds, that's two different speeds. And any airplane will have a best range speed and a best endurance speed, right? And the best range speed is always going to be a little faster. But any airplane will have those two speeds, whether you want it or not, right? It's just the way the physics works. And what's that's determined by is their different points on the drag polar. So what I've done over here, when I went and I ran VSP Aero with more points, it was just so that we could generate this nice smooth curve. And this smooth curve is what we call a drag polar. And it's almost always shaped like a parabola. And earlier we only had 3 points on it, boom, boom, boom. And while you can fit a parabola to 3 points, it doesn't look like a parabola all the time, right? It just looks like 3 points. So that you guys would believe me that it was really a parabola, I went and I ran a bunch more points. And so now everybody agrees it looks like a parabola, and we could go back to just looking at 3 points on it again. But we've got this parabola, and I'll go a little bit of a tangent. The reason we call it a drag polar, if you're interested, and I'll even go more off topic. The first person who called it a drag polar was a Frenchman who was an amateur aerodynamicist. He in fact invented his own wind tunnel, and today we call that wind tunnel, we name it after this person. He's more famous as a civil engineer because he built the Eiffel Tower. And so the Eiffel style wind tunnel, Gustave Eiffel was in fact an amateur aerodynamicist, and he's the first one who called a drag polar. And the reason it's called a drag polar is that when you plot it in this way with lift on the vertical axis and drag on the horizontal axis, if you were to plot the total resultant aerodynamic force on a body, whether it's a wing or a plate or an airplane, and you were to plot it in polar coordinates, you get this. So if you actually were to look at, and again, these axes are weird, right? The x-axis is much, much, much more zoomed in than the y-axis. But if you drew a line from the origin at 0, 0 to a point on this curve, and you figured out the angle with these at equal axes, and in fact we can force them to be equal axes. Let's we'll do this real quick. Everything's real quick. So here we are. Here they are in equal axes. And so if you were to draw a line from here to any point on this curve, the magnitude of that line is the magnitude of the total resultant force, and the angle that that line makes is the angle with the free stream of the resultant force with the free stream. So Gustav Eiffel, with his wind tunnel, plotted the total resultant force in polar coordinates and called it a drag polar, and that's what we still use today. But typically the axes will be super zoomed in because it looks better that way. But here they are. We've got the x-axis is 10 times as big as the y-axis. Now, there's still very important. If you take a line and you draw from this origin, and you look for the point tangent to this curve, right? If you imagine that's going to be right about here, I think that's going to be the point tangent to the curve. That is the best L over D point. That is the maximum lift to drag ratio. Okay. And you can just think about that, right? Clearly, any line that's to the right of that is going to have less drift and more drag. And any line that doesn't touch the curve, well, it's not on the curve. So, what you need to do, and this balances a lot of different things in aircraft design, but you need an estimate of the weight of your aircraft. Let's say that you think you can come in at 35 pounds, right? And that's with all your structure and all your sensors and all your batteries and everything else. You think you can come in at 35 pounds. And then you need to figure out, well, what area do you think the wing needs to be? And, to make the math easy, let's say it's 10 square feet of area. So at 35 pounds and 10 square feet of area, you have a wing loading, which is just that ratio of 3.5 PSF, 3.5 pounds per square foot. So when you look at the CL equation, oh, I haven't been sharing my screen, have I? Oh, no, it is.
No, you have been.
Once again, I was afraid the other way. So when we look at, let me just do something super, super quick here. Okay, all I'm doing here is I just wanted to be able to write something. So I just said your weight is 35 pounds. And let's say your reference area, your wing area is 10 feet squared. And so your wing loading, which is W over S, is going to be 3.5. And that's going to be pounds per foot squared. Or sometimes we call that PSF, pounds per square foot. Your lift coefficient equation, CL, is equal to W over Q times S. For Q is your dynamic pressure is 1/2 rho times V squared. Okay. So you'll notice CL, this W over QS, well, W over S is your wing loading over Q. And here Q, rho is your density, which really means your altitude. Right? Whether you're are you looking for things in the Himalayas or are you looking for things at sea level, right? That's going to determine your density. And your V squared, right? That's obviously your speed. So remember I said earlier, pitch for speed, right? As a pilot flying along, you're trying to trim for some CL. You control CL by controlling trim. Let me put it that way. You have some control over CL as a pilot. And you want to change your speed, your V squared. I mean, there's other ways you could trim, right? You could trim by throwing weight overboard. You could say, look, we need to trim this airplane to a different speed, and so we need to get lighter. So you throw stuff overboard, right? That's not very sustainable. Passengers don't like it, and it's hard to go the other way. It's hard to pick up and add weight while you fly. right? So this is one of these situations where, as an aircraft designer, oh, and also wing area, right? You could imagine you could send a wing walker out with a saw and just cut off pieces of the wing, right? You could change your S during flight, right? That's a terrible idea. But so you can think as a pilot, if you want to trim the airplane to a different speed, if you want to change V, right, you can't change S. Rho is what it is. Okay, you can change altitude, but you can't demand, I want higher rho, I want lower rho, right? You're kind of at the mercy of rho. And so if you want to change speed, if you want to change how fast you're flying, as a pilot in this equation, the only thing you can change is CL, right? And that's by trimming the airplane. As an engineer, I can change W and I can change S, right? As an engineer who's designing an airplane that doesn't exist yet, then I can change those variables. And as an engineer, what we're trying to do, remember when we looked at our drag polar, we're trying to figure out, let's say we want to fly at the best L over D speed. Notice that tangent point that I'm talking about, it occurs at one very particular CL. So our best range speed, remember I said that best range speed and best endurance speed was a particular speed, right? So they're a particular point on the drag polar, they're a particular speed, and it's only the speed we want it to be if it matches the CL at the wing loading and the speed and the density that we all want it to be. So this is one of those things about aircraft design is that, you know, you've got to do it all at once and it's all iterative. So if we look instead on this chart and we look at the X as CL and we look at the Y as L over D, and we let it figure out the axis limits, this is pretty typical of what you're going to see, and this is ugly. And part of the problem right now is that this analysis that we did does not have a believable amount of parasite drag. And the Reynolds number, the CF equation that we've got right now, this airplane wouldn't be up at 1 million Reynolds number. We'd be more, I mean, that's at 10 million even. So let's change it to 100,000. Run the solver again real quick. Again, way too many points. And come over here to our sweep. X is CL, Y is lift to drag. And that's going to be a bit more reasonable. That's still probably we need more drag. So we're under predicting drag right now. And frankly, this chart will always under predict drag. And let me just give you an example. On a very clean airplane like this, on something like a blended wing body or a flying wing, if you have fixed landing gear, and so your wheels and your struts are all hanging out in the air for the whole flight, that fixed landing gear probably doubles your drag. Okay, it's huge. And I don't know if you noticed, but do you see any landing gear in this model? Right, there's no landing gear. So when we look at our drag polar, on this airplane, the intercept of this polar, this lowest point, is what we call CD naught, CD 0. That's our parasite drag. This intercept is caused by the friction of the air on the wing and things like landing gear, right? So when I say that we double the drag, that means we take this whole parabola and we shift it to the right. We shift it big time over here to the right to get that CD naught up. Whereas the curvature, this parabola shape, that's caused by induced drag. So that's caused by the lift, and that's what we're actually capturing with this physics in Vorview, is we're able to understand that. And so this balance, if you notice now, if I draw the tangent line, now that we have more parasite drag in this case, when I draw that tangent line, it's now hitting our best L over D, it's somewhere between a 0.2 and a 0.3 CL. Well, let's see if that matches. If we look at our L over D, it's peaking between a 0.3 and a 0.3 CL, somewhere right in there, right? So our best endurance point and our best range point, there are going to be some points along on this curve in order to dial that in. So, and you guys, you're giving me some ideas for changes to make to VSP right now. So what I'll say is you'll need to iterate, and you'll need to think about what you can change as an engineer, right? As an engineer, you can change the wing area, and you can match that to the speed you want to fly and to the wing area you have, and that'll help. It'll actually move this peak in L over D left and right. Okay, by changing the wing area, you're actually going to move this peak left and right, and this horizontal axis, right? CL, well, we control that controls speed, so that'll control the speed left and right. And you'll need to figure out, what CL are you targeting, and therefore, what LRD are you targeting, and what speeds are you targeting with your ConOps. The sensor that John's working with you on, if you flew by at 500 miles an hour, he might not see anything. So your sensor is going to determine how fast you need to fly. Do you need to fly really slow, or can you get away with flying faster? So those all factor into the ConOps and determining what your target speed is. And then, as I said, then you've got to be able to use reflex or camber to twist the airplane to get it to trim out at the speed you need. And I recognize that I've fed you guys with the fire hose, and I don't know if I've clarified things today or if I've just overwhelmed you, but
You know what? Luckily, it's recorded, so I'm sure, like, as they make progress with this aircraft, they can reference back to this video, and a lot of stuff that you have talked about would probably make more sense. But I think we have one last question, which I think is kind of something that Mark Page had suggested everybody do. And here it is. It is Mark Page suggested the interns try mixing a bit of a Mark Drella F3J airfoil with his baseline airfoils. How can OpenVSP be used to create new airfoils from linear combinations?
So we don't have a ready-made blend two airfoils together functionality. That would be a cool thing to have. So we have a bunch of airfoils, which is what we call catalog airfoils, right? They're families of airfoils that we generate from the equations. So, a bunch of smart people 70 years ago came up with equations for these different airfoils. And so we have a bunch of those built in, and then we have the ability to read in a file. We also have and let me go. So here we have one of these airfoils, and let me show this airfoil. So it's not going to show up. Let's come in here. Let's turn off that. So now we're looking at the root airfoil, trying to look as close as that as we can. And we're here at the root. So that's a NACA 0012. So it's 12% thick. The maximum thickness is at 30%. So that's an airfoil. There's this button down here that says Fit CST. So CST stands for Class Shape Transformation. And it is a curve fitting technique that was developed by a Boeing engineer. And we'll talk about her in a moment. But so when you hit Fit CST, what we did in that instantaneous moment was we fit a 7th degree curve, a 7th degree CST curve to both the upper and lower surface to a best fit to what we had before. So this is an approximation of that NACA airfoil. This is the best approximation you can do with 7th degree curves. Now, there's a couple of buttons here. You can say demote. And what we're going to do when we demote is we're going to take the 7th degree curve and we're going to come up with the best approximation of it with a 6th degree curve, right? So we go to 6th, and we go to 5th and 4th and 3rd and 2nd, right? And as we come down, you'll notice that the curve, it's not looking as good as it was originally. That's as low as we can go. And it's subtle, but there's differences. And promote, well, we can, this isn't updating. What's going on? No, it is. Well, let me go back and let me put this bump in, and let me demote that, right? And you can see as I demote, that bump gets washed out. Okay. And as I promote, well, promotion we can do exactly. So I can represent that curve exactly. You know, there's a 14th order curve, and that's exactly whatever the other thing that I demoted down. What's the point of this? What I think would actually work, let's see if we can try it. This is a little bit crazy. Let's change this back to a, let's change it back to a 4 series. And for fun, we've got a 0012 here at the root. And let's go out here to the tip and let's make this a 4412. And you can't, let's change this to none. So, so there we go. So there's a 4412 out at the tip and a 2412 at the root. And we're gonna get rid of our twist and our camber, and we're just gonna line them up. So there they are. We have a root airfoil and a tip airfoil, and we're only doing that just because we need a convenient place to put 2 airfoils. And what I'm gonna do, I'm gonna split this wing in half. So now we have a 3rd airfoil in between, and it's currently initialized to the one out here at the tip. I've never tried this. We're gonna see if it works. So we're gonna come down here to the 0012. Let's go ahead and initialize this one to the 0012 also. And then we've got the 4412 out here at the tip. So what we're gonna do first, and I don't want this to be too crazy, so we're gonna only do it with, say, 5th order. I'm gonna fit each one of these to a 5th order CST. So now they are class shape transformation approximations of this. And I believe this airfoil is in fact linear in all these terms. So to do a linear combination, what I think we can just do is if we average the coefficients for the tip airfoil and the root airfoil, we should get the linear blend. So VSP has a cool new feature where if you take, so now this one's already initialized to the first one. So we want to average whatever its current value is with this value out here at the tip. So I'm going to come out here to the tip, and I'm going to take this first coefficient. I'm going to copy that with a Control C. Then I'm going to come in one. I'm going to go to this first tip. Recently, VSP got the ability, you can actually do little algebraic expressions in the boxes. So if we add that in and we divide by 2 and we hit enter, we just change that first coefficient to the average of the other 2. So I'm going to do this. This is completely ridiculous. What you should really do is you should do it in MATLAB, or you should do it in Python, and you should just read in the airfoils and do the linear combination, then read that into VSP, right? It's going to be much easier to do that way. But I'm going to see if we can do it. So we're going to copy this. We're going to come in. We're going to average it. We're going to go out. We're going to go to the third one. Come back. Average it. Go out. We're down to the fourth one. Okay, we're up to the 1, 2, 3, 4, fifth one. And last one. I think if I continued and I did that for the bottom surface also, I think we'd find that that is in fact the linear combination, the average between the two. So that's slightly crazy, but it would work.
That is pretty interesting. Now, you've been so awesome, Rob. It makes me want to go back to school and get a degree in aerospace engineering.
Well, I recommend it. I mean, I've had a blast being an aerospace engineer. I couldn't imagine anything more fun to do. So,
Yeah.
aircraft design is, I'll just say that to me, it's a very beautiful problem. It's got amazing challenges. It's amazing because, right, it all boils down to F equals ma, right? It's all some very simple fundamental equations that then when it comes together to actually make an airplane and make it do what you want and perform the way you want, there's incredible complexity that sort of this complexity emerges out of some incredibly simple physics and simple things. And it's really a beautiful problem that way.
Yeah, I think it's I can see it both as like engineering and art coming together. Then of course, the physics, the science aspect of it as well. Combination of it also, you're kind of like touching base on a lot of different disciplines as an aerospace engineer.
Well, I would say that to me, that's the definition, intellectually in terms of the classes we take and the content, aerospace engineering and mechanical engineering are very, very similar, right? They're our closest academic cousin. And to me, the fundamental difference between those and the way I've always explained it to people is, and of course I taught senior design, so I'm incredibly biased, right? I taught aircraft, but in a mechanical engineering senior design in a capstone class, it would be sacrilege, right? It would be never done to not actually build something, right? It doesn't matter if it's, 2 gears and they need to take a really heavy load and be really quiet and last for 1,000,000 hours. You're going to design those gears and you're going to go build them, right? Because it's in mechanical engineering senior design, you build it. That's what you do. In aerospace engineering, it would be sacrilege not to look at the entire system.
Yeah.
Right? We have this system level perspective that is the thing that makes us different from MEs is we care about the whole vehicle, not just part of it. And whether that's a satellite or an aircraft, and what that means is in senior design, we usually don't build it because, a big airplane, it may take Boeing 6 years and $4 billion in debt to develop an airplane, and you're not going to do that every year in a senior design class. So you've got these trade-offs pedagogically, but the important thing that really comes home is aerospace engineering is always looking at that system and the big picture and pulling all the disciplines together. And there's other examples of this. I'd say, biomedical engineering is a lot like mechanical engineering, but again, specialized to one particular problem domain where, they're only interested in biomedical applications, even though it has lots of EE and lots of ME and lots of all these contributions to it. It's a domain specific thing. And that's what aerospace is I think it's important to it that the system levels part of our definition.
Yeah. Well, thank you so much. I mean, this was really helpful. I know it was probably a lot more than I was expecting, but I feel like I just attended one of your senior classes or something.
Well, I'm not a professor anymore, so
Well, you're very, very, very good. So it shows you love what you chose to do. Joey or John, do you guys want to add anything?
Oh, I really enjoyed this presentation, Rob. Thank you so much. Of course, I'm not an aerospace guy, but I've received a treat this afternoon. As opposed to say. I
Well-
had a comment in the notes that one of the problems with electrical engineering is that almost everything that we do is virtual, whereas mechanical engineers and civvies and aerospace engineers, they make stuff that you can touch or ride in or jump up and down. And I've always envied that about those other.
Well, you know, it's funny when students would choose, do they go on the aircraft design track or the spacecraft design track? It was amazing to me how many of the students would choose because, for better or for worse, if you design a satellite, right, you launch it and nobody ever sees it again. and it was amazing to me how many students would say they wanted to work on something that they could show their friends and they could show their family and they could show their parents. And while stuff that goes into space is cool, you never see it again.
Right.
Yeah, it's really true. Years ago, I visited, I think it was Cal Poly Pomona, and they have a CubeSat program there. And the students they had so much enthusiasm for it. They were crawling all over that project. And I've never seen that kind of enthusiasm in electrical engineering. And, you know, we do some cool things, but boy, having physical artifacts is really something.
Yeah. Well, I'm sure Pomona has a CubeSat program. The origination of CubeSat was at Cal Poly San Luis Obispo. So
that's it. See, San Luis Obispo. That's the place.
Yeah. So yeah, that's you were probably there for one of the CubeSat workshops. So that's Jordy was the department chair that hired me, and he's the one who, along with the guy from Stanford, wrote the standard for CubeSat.
Oh, that's pretty cool. Small world.
It is. Well, thank you guys for lasting this long with me. It's been fun.
Yeah. Joey, you were going to say something, I think.
I just want to thank you because usually I come into talks like this just wanting to take away 2 or 3 key points to apply to what I'm doing with this project. But I think it's safe to say I took away a lot more key points than that. And it was very, very helpful. And I'm excited to, as soon as I get off this call, I definitely want to start working on a couple of things. You have the wheel. So thank you.
Cool. Well, good luck to you guys. I wish you the best.
Thanks so much, Rob. We'll be in touch with you.
All right. Thanks.
All right. You guys have a good weekend. Take care. Bye.